Everyone is using MCP servers these days. They're connecting AI agents to databases, Kubernetes clusters, GitHub repos, cloud resources, you name it. MCP is becoming the standard way to give AI tools access to external systems. But here's the question. How should you actually run those MCP servers? The documentation typically shows you one way, running it locally with NPX. But is that secure? Is it scalable? Can your team share it? What about production? There are actually multiple deployment options, each with different trade-offs. So here's what we're going to do. I will show you 4 different ways to deploy MCP servers, from the dead simple to the enterprise ready. We'll look at local execution with MPX, Docker containers, Kubernetes deployments, and operator-managed resources. Plus, I will cover a few notable cloud platforms like Fly.io, Cloudflare Workers, and AWS Lambda. For each approach, I will show you exactly how it works, what problems it solves, and what new problems it creates. We will explore all of this through practical examples. I will use my DevOps toolkit as the MCP server we are deploying. Not to sell you on the project, but because I need a real MCP server to demonstrate those patterns. And this one works with Kubernetes, vector databases, and all the complexity we'll need to see. Everything you will learn applies to any MCP server you want to run. Here's another challenge. AI agents, even when they're wrapped inside the MCP protocol, need to authenticate with web services and access APIs. You could hardcore credentials, but that's risky. Environment variables? Well, still not ideal. Building your own credential injection system? Well, now we've got another problem to solve. That's where the sponsor of this video comes in. 1Password and Browserbase launched an integration for secure agentic authentication. You connect your 1Password vault to Browserbase director in under 3 minutes. When your agent needs credentials, they're injected just in time at runtime. The agent doesn't see them, log them, or store them. The injection includes human-in-the-loop authorization. When an agent tries to authenticate, you get a push notification for approval. Credentials are automatically mapped to the right services, and there's an audit trail that logs item IDs and timestamps without exposing the actual secrets. If you want to learn more, check out browserbase.com. And now, back to MCP deployments. Let's start with the simplest way to run MCP servers, executing them directly on your local machine. This is typically the default approach you will find in most MCP documentation. Whether it's MPX for JavaScript servers, Python for Python-based ones, or whatever runtime the server needs, doesn't matter. You just run the command directly. It's what's usually documented, often because authors assume you will figure out how to transform it into something better, or because they were too lazy to show you the alternative. One of the two. Let me show you what this looks like. Here's the configuration file that tells Claude how to run my .ai MCP server locally. I'm using my own MCP server for this demo since that's the one I'm working on in the penalty of this video. But the same, and I repeat, again, the same principles apply to any MCP server. That's pretty straightforward. We're telling Claude to use NPX to run the MCP server, passing it the package name and the environment variables it needs. Notice that quadrant URL over there? That's our vector database dependency that needs to be running separately. We already started it during the setup, but in a real-world scenario, you would need to manage that yourself. The point is that not always there is only MCP server. There are sometimes dependencies of that MCP server. Now, let's fire up Claude with this configuration and see it in action. Once Claude starts up, let's test if the MCP server is working by asking it to list the patterns available in that MCP server. There we go, perfect. The MCP server is running locally and Claude can communicate with it. We can see the patterns that are stored in quadrant. Everything works as expected. Now, this local approach might seem great at first, but there are some serious trade-offs you need to consider. This is typically the default, and sometimes the only documented way to run an MCP server. But that does not mean it's the best approach for your situation. First of all, adding dependencies is a pain in the ass. See how we need quadrant running separately? In a more complex setup, you might need multiple services, databases, or other dependencies. Now, agents typically start the MCP server when they launch, and shut it down when they exit them. But if you wrap everything in a script to handle those dependencies, you might end up with zombie processes. The agent might kill the script but leave all the child processes running. Before you know it, you'll get a bunch of orphaned services eating up your resources. Then there's the installation requirement. You need Node and NPX installed on your machine for this JavaScript-based MCP. If you're using a Python MCP, you need Python. Ruby MCP, you need Ruby. Your machine starts to become a mess of different runtimes and package managers. But here's the biggest issue. There's absolutely no isolation. This MCP server has direct access to your entire laptop. It can read your files, access your network, and do whatever the hell it wants. Sure, you might trust the MCP server code, but do you trust all its dependencies? All their dependencies? It's a security nightmare waiting to happen. Look, this might be the easiest approach, aside from needing the right runtime installed. It might be what's documented everywhere, but let's be honest, it's potentially the worst way to run MCP servers. You've got dependency management issues, process lifecycle problems, and zero, and I repeat, zero isolation. There has to be a better way, right? Let me show you some alternatives that address those problems. Now, let's try a better approach, running MCP servers in Docker containers. And here's the thing, at the end of the day, an MCP server isn't that different from any other server. Sure, it uses STD-IO instead of HTTP for communication, but it's still just a server that needs to run somewhere. And how do we typically run servers locally these days? Docker. It gives us isolation, better dependency management, and we don't need to pollute our machines with various runtimes. Let me show you how this works. The configuration is slightly different now. Instead of running NPX directly, we are telling Cloud to use Docker Compose. See the difference? We're using Docker Compose run as the command. The Docker Compose file handles all the complexity. Starting quadrant, setting up networking between containers, managing volumes, all that stuff. The --rm flag ensures containers are cleaned up when we're done, and remove orphans takes care of any leftover containers from previous runs. Now, let's fire up Cloud with this Docker-based configuration. This time, let's test it with a different command. Instead of listing patterns, we'll ask for Kubernetes capabilities that the MCP server has discovered, just to vary a bit. There we go. Excellent. The Docker-based MCP server is working perfectly. It discovered a bunch of capabilities from our Kubernetes cluster. Now, notice how everything just works without us having to manage quadrants separately or worry about process lifecycles. Docker Compose handles all of that for us. So, what have we gained with this Docker approach? First and foremost, we got proper isolation. The MCP server runs in its container with controlled access to resources. Unless you do something silly like mounting your entire file system or running containers in privileged mode, you're much safer than with the direct local approach. Everything runs in containers, which means you don't need to install Node, NPX, Python, or whatever runtime the MCP needs. Just Docker and you're good to go. All the dependencies are bundled together in the Compose file. Quadrant, the MCP server, networking between them, it's all defined in one place and managed as a unit. But here's the thing, it's still running locally. This is still a single user setup on your machine. Now, you might be thinking, can't I just run Docker on a remote server? Sure, you could expose Docker's API over the network, but that opens up a whole can of security worms. You would need to manage TLS certificates, authentication, network access. It gets complicated fast, and you're basically reinventing infrastructure that already exists. There's a better way to go truly remote, with proper multi-user support, high availability, and all the enterprise features you might need. Let me show you what it looks like. Time to go truly remote. Here's where we make a fundamental shift. Think about it. Running MCP servers locally is like local development. Everyone spins up their own instance, manages their own dependencies, deals with their own problems. But what if we could run MCP servers like production services? Deploy them once, properly, and let the entire team or company connect to them. That's exactly what Kubernetes gives us. So this isn't just about containerization anymore. It's about turning MCP servers into shared organizational infrastructure. Instead of every developer running their own instance of various MCP servers, we deploy them once, to Kubernetes, and everyone connects to the same properly managed services. Whether it's my .ai server or your custom MCP for internal tools or that third-party MCP for cloud resources, the approach is the same. So let's deploy an MCP server to Kubernetes using Helm. I'm using my .ai server as the example, but as I already said, everything you see here applies to any MCP server you want to run in production. Did you notice something important here? I am running these commands, not Claude. This is fundamental shift. In the previous examples, the agent was responsible for spinning up MCP servers when it started and shutting them down when it stopped. The configuration told the agent how to launch the server. Now we separated those responsibilities. A human or GitOps or your CI/CD pipeline deploys the MCP servers to Kubernetes just like any other production service. The agents just connect to them. They don't manage their lifecycle anymore. Let's see what Kubernetes created for us. There we go, perfect. We got the MCP server running as a deployment, Quadrant as a stateful set for persistent storage, services for internal communication, and an ingress exposing it all at specific URL. This is proper production infrastructure running independently of any agent. Now let's look at how agents connect to this remote MCP server. Look at this configuration carefully. We are not telling Claude to run the MCP server anymore. We are telling it to connect directly to the already running MCP server at that URL using HTTP transport. The type HTTP tells Claude to use HTTP transport to communicate with the remote MCP server, and the URL points to our Kubernetes ingress endpoint. This allows Claude to communicate directly with the MCP server running in Kubernetes over the HTTP. This is clean, direct connection without any local bridge processes or protocol translation. The agent speaks HTTP, unlike the default, which is std.io, it speaks HTTP directly to the remote MCP server. So let's connect Claude to our MCP server, remote one, and check its status to make sure everything's working. Excellent. We're connected to the MCP server, remote MCP server running in Kubernetes. Notice that it shows the Kubernetes version, Quadrant is connected, all the services are healthy. This is the same MCP server we deployed, but now multiple users can connect to it simultaneously. So what have we achieved with this Kubernetes approach? We got real isolation through Kubernetes namespaces, RBAC, and network policies. The MCP server can't access your laptop anymore. It's confined to its namespace with only the permissions you explicitly granted. Everything still runs in containers, so there's nothing special to install on developer machines. But now we also get all the Kubernetes goodies. Higher availability, if you want it, auto-scaling, security policies, audit log, the whole shenanigans, the whole enterprise package. Most importantly, this is truly remote and multi-user. You deploy the MCP server once, and your entire team connects to it. Everyone shares the same patterns, the same capabilities, the same configuration. It's like the difference between everyone running their own database locally versus connecting to a shared production database. Now, to be frank, the setup is more complex than local deployment, but that's the nature of production infrastructure. You need the Kubernetes cluster, Helm charts, ingress controllers, and so on and so forth. But here's the thing, you do this setup once and everyone benefits. It's infrastructure, not something each developer needs to figure out. Still, there's another approach using Kubernetes operators that claims to simplify MCP server management. Let me show you what happens when you add ToolHive to the mix. StackClock created an operator called ToolHive that promises to simplify MCP server management. The idea is that ToolHive manages MCP servers as Kubernetes custom resources with additional features like permission profiles and resource management. Let's see if it actually delivers on that promise. ToolHive treats MCP servers as first-class Kubernetes citizens. Instead of deploying standard deployments and services, you create an MCP server resource and the operator takes care of the rest. Or at least that's the theory. So let's deploy the same MCP server using ToolHive instead of standard Kubernetes resources. And notice the deployment method equals ToolHive parameter in the Helm command. That's important. And there we go. There's our MCP server custom resource instead of a regular deployment. Now, let's dig deeper and see what this custom resource actually contains. That over there is a lot of YAML. The key things to notice is that it's got the container spec embedded in pod template spec. It specifies transport as streamable HTTP, and in the status you can see the proxy URL. ToolHive took our MCP server definition and created the necessary pods and services. But wait, notice the proxy mode set to SSE, that server sent events. And here's the problem. SSE transport is deprecated in the MCP protocol as of November 2024. MCP moved to streamable HTTP instead. So ToolHive is using a deprecated transport mode. Not exactly filling me with confidence about this operator's feature. But let's continue. Let's see all the resources that were created both by ToolHive and by our Helm chart. Look at all those resources. The Helm chart created the MCP server custom resource, Quadrant, the ingress, and other supporting resources. Then ToolHive operator saw that MCP server resource and created additional pods and services like .ai MCP-O and MCP.ai MCP proxy. So we've got resources created by Helm and resources created by ToolHive based on what Helm created. It's layers upon layers of abstraction. Now, here's the interesting part. Let's see how the client connects to this ToolHive managed MCP server and whether it's any different from our standard Kubernetes approach. Hey, notice that the configuration is identical to our standard Kubernetes deployment. We're using HTTP transport to connect directly to the MCP server. ToolHive's proxy supports both STDIO and HTTP transports, but HTTP is clearly the better choice. According to ToolHive's own performance testing, STDIO transport has severe performance limitations. In their tests, with 50 concurrent requests, only 2 succeeded. The STDIO implementation is unsuitable for production use. So, by using HTTP transport directly, we get better performance and eliminate the complexity of STDIO to HTTP translation that would otherwise be needed. So, let's connect to the MCP server anyway, just to verify it works. And there we go. It works. The MCP server is running and accessible. But let's be honest about what we actually achieved here. The end result is almost the same as when using standard Kubernetes resources, except now some of them are created by the operator. We still need the ingress, we still need to manage secrets, we still need supporting resources. The ToolHive custom resource didn't eliminate complexity, it just moved it around. That's why I had to wrap everything in a Helm chart anyway. So, what's the theoretical advantage of ToolHive? The main selling point was supposed to be better MCP server lifecycle management through Kubernetes operators. But in practice, it's just another layer of abstraction and doesn't solve the fundamental deployment challenges. The STDIO transport it supports has catastrophic performance issues, which is why we're using HTTP transport anyway. At the end of the day, running MCP servers is just like running any other HTTP server. You deploy them, you expose them through an ingress, and connect to them over HTTP. ToolHive adds a custom resource abstraction on top, but I'm honestly not seeing the value. It's using deprecated SSE mode, and it adds another layer of complexity without clear benefits. So, if you prefer using operators and custom resources, sure, ToolHive is an option. But given its limitations and the fact that it doesn't actually deliver on its main promise, I would stick with standard Kubernetes deployments. At least those are straightforward and don't pretend to solve problems they can't actually solve. Let me show you a few other deployment options before we wrap it up. So, before we wrap up, let me quickly run through some other ways to deploy MCP servers. There's a whole ecosystem emerging around MCP deployment, and while I've focused on Kubernetes because it's vendor agnostic and production ready, you should know what else is out there. FlyIO takes an interesting approach. They run MCP servers as tightly isolated VMs, which they call fly machines. You can deploy with a simple fly MCP launch command, and they handle authentication and routing for you. They support both single tenant, each user gets their own app, and multi-tenant patterns. It's pretty slick if you're already in their ecosystem. It is. Then there is Cloudflare Workers. that went all in on MCP. They provide all-out authentication, out of the box, zero egress fees, and CPU-based billing that's perfect for streaming connections. You can deploy MCP servers as edge functions that run close to your users. Their Workers MCP tooling handles the protocol translation for you. If you're looking for truly serverless MCP, this is probably your best bet. Probably. AWS Lambda offers the AWS serverless MCP server. It works technically, but the developer experience is rough. Cold starts are painful, and the STD-IO transport has serious performance issues on Lambda. Then there is Vercel that lets you add MCP endpoints directly to your Next.js apps using the MCP handler package. If you already have Next.js applications on Vercel, this is the path of least resistance. But watch out for their egress charges and memory-based billing for idle connections. Watch out. Railway keeps things simple. It's a deployment platform that just works without needing platform engineers. Deploy your MCP server like any other app. Nothing fancy, but sometimes that's exactly what you need. Then there is Podman with MCP server implementation that deserves a mention, though it's not really a deployment solution. It's an MCP server that lets AA agents manage Podman containers on your local machine. Think of it like the Docker MCP server, but for Podman users. Still local, still has all the same limitations we discussed earlier. And here's the thing about all those alternatives. They each have their niche. Fly.io is great for multi-tenant isolation. Cloudflare excels at edge deployment with minimal latency. AWS Lambda, well, it exists. Vercel makes sense if you're already there. But they all have one problem: vendor lock-in. You pick Cloudflare, you're stuck with Cloudflare. You pick AWS, you're stuck with AWS. Most of them are still figuring out MCP. They are still not sure. The implementations are evolving. The performance varies widely, and the developer experience ranges from decent to painful. That's why I keep coming back to Kubernetes. It's vendor agnostic. You can run it anywhere: AWS, Google Cloud, Azure on premises, or that server under your desk. The deployment patterns are mature, the tooling is solid, and you're not betting your infrastructure on a single vendor's interpretation of MCP. Unless you're a small company with just a few apps, or you're already deeply committed to a specific cloud vendor, Kubernetes remains the most flexible option for production MCP servers. But hey, at least now you know what's out there. Choose what works for your situation, not what I tell you to use. Don't do it. All right, let's take a step back and look at what we've covered. We've gone through a journey of MCP server deployment options, from the simplest to the most complex, from local to remote, from vendor-specific to vendor-agnostic. We started with local NPX execution, the simplest approach, sure, but it comes with zero isolation, dependency hell, and security nightmares. Your MCP server has full access to your machine, and managing dependencies becomes your personal problem. It's what documentation shows you, but that doesn't make it right for production. Then we moved to Docker locally. Better isolation, true. Everything in containers, great. Dependencies bundled together, but it's still a single user setup on your machine. Fine for development, not so much for team collaboration. Next came Kubernetes with standard deployments. This is where things get serious. Proper production infrastructure, multi-user access, high availability, all the enterprise features you would expect. Deploy once, everyone connects. It's like the difference between running a database on your laptop versus having a proper database server. We also tried Kubernetes with a ToolHive operator, which promised to simplify MCP server management, but ended up adding complexity without clear benefits. It uses deprecated SEC mode and adds another layer of abstraction without solving fundamental deployment challenges. Finally, we looked at cloud platform options. Check them yourself. So, which one should you actually use? If you're developing an MCP server itself, Docker makes sense. You need to test locally, iterate quickly, and see immediate results. But let's be clear, this is for MCP server developers, not MCP server users. For any team or company setting, the local options are ridiculous. Why would every developer spin up their own instance of the same MCP servers? That's like asking everyone to run their own Jira or Slack instance. You want shared services that everyone connects to. That means Kubernetes or one of the cloud platforms. For production workloads, Kubernetes is the answer, unless you have a damn good reason to avoid it. It's vendor agnostic, battle tested, and gives you all the operational capabilities you need. Deploy each MCP server once, and your entire organization can use it. That's how infrastructure should work. Now, if you're already committed to a specific cloud vendor, their native solutions might make sense. Got everything on Cloudflare? Use Workers. Deep in AWS? Maybe Lambda will work for you eventually. But understand that you're trading flexibility for convenience. The key insight here is that MCP servers are just servers. They're not special snowflakes. They need to be deployed, exposed, and accessed like any other service. And just like you don't run your own copy of every microservice in your company, you shouldn't run your own copy of every MCP server. Share the infrastructure, share the costs, share the maintenance burden. Now, if you want to experiment with those approaches, especially the Kubernetes deployments I've been showing, check out my DevOps AI Toolkit project. Why not? It's the MCP server I've been using throughout these examples. Start the repo. If you find it useful, open issues. If something is not working, most likely it's not. Submit PRs if you want to contribute. All in all, the MCP ecosystem is still young, and we are all figuring this out together. The more we share what works and what doesn't, the better these deployment patterns will become. So don't just consume, contribute. Help make MCP deployment less painful for the next person who comes along. Thank you for watching. See you in the next one. Cheers.